In the previous class, we concluded with the concept of convolution sum, okay, where Hn, the impulse sequence coefficients, are multiplied with a series of x, series of inputs, okay, and its delayed version of inputs. Xk minus n, it is the various delayed inputs are there. They are multiplied with the filter coefficient or impulse response of the filter to give us the output. Now the question is how we can get various samples of the inputs or various delayed versions of the input. How we get it practically? Let's see this thing. Now first we consider, to start it in a simple way, we consider a D flip-flop. Okay, a D flip-flop. You already know flip-flop. It is H triggered. Okay, now these flip-flops are, some of the flip-flops are connected in series, in cascade. Okay. Okay, these are there. And all these H triggered clock lines are connected common. Okay. Now what happens? This clock, it is just a square wave pulse, you know, a pulse train. And age means here it is a positive age or rising age. So at every age, the flip-flop will be active and input will go to the output. D input will go to the Q output. So at this rising age, input will go to the output. At the next rising age, another input of the flip-flop will go to the output. So at every rising age, this will happen. Now we consider our first rising age, where we get one sample. So one signal will come here, this input. Say this is our x0. We are considering. Just I am writing x0 here. Okay, so x0 will be available. Okay, so something will be, some x0 will be available. Somehow it is coming from the previous flip-flop or something like. In the next rising age, what will happen? Okay, the next sample x1 will come. And by this time, this x0 will go to the output. X0. In the third rising age, and okay, our this x0 will go here. We'll get x0 here, and that x1 will come here. And a new sample x2 will come. Again, in the fourth rising age, this x0 will be going here. That is our x0. That x1 will be going here. And that x2 will be going here. And by this time, a new sample x3 will come here. So this way, in general, we can say that we will get xn, okay, or xk rather, I am writing xk. Then here we are getting what? The previous sample. Say it is x3, x2, x1, x0. In the next rising age, x4, x3, x2, x1, this way. So it will be xk minus 1, xk minus 2, xk minus 3. This way our samples will come. Okay, our samples will come. This is the present value. Xk is the kth value, is the present value. K minus 1 is the past value that was stored here. Now after one rising age, this stored value is now coming here. In the next rising age, that goes here. So the previous value comes here, a new value, relatively new value is taking the position here. So as we go towards the right side, we will go on getting the past values of the samples. So this is the past value, it is the past of past, it is the past of past of past value. So this way will go. And xk will be the present instant always. Now, but these samples are 1-bit samples. They will be either 1 or 0. Now, if we connect 8 flip-flops together, so connecting 8 flip-flops together in parallel, what we get? An 8-bit data will be constructed, okay, in parallel at every stage. So 8-bit input will come here, and all these 8 flip-flop will be triggered by the same clock here, every stage. 8-bit shift register is constructed. Okay, this holds 8-bit data. So our XK will be 8-bit data because 8 parallel such parallel flip-flops are there. XK minus 1 is another pass data which is of 8-bit length. It again is stored in another flip-flop, 8 flip-flop, okay, or another shift register. So the third sample is also holding another shift register this way. So at every stage we get set of 8 flip-flops, and 8 shift, and our shift register is constructed. So ultimately what happens? One shift register. So if we consider a shift register, this shift register is
parallel connect করা হবে না cascade?
No, parallel. These 8 flip-flop will be connected in parallel. Another 8 flip-flop will be connected in parallel. Another 8 flip-flop will be connected in parallel. So 8-bit data will go here. Then again 8-bit data will go at every stage. Now each such shift register will be just connected in cascade. So one shift register, so it is a combination of 8 flip-flop in parallel. Then another shift register, then it is also connected there in cascade. So they all will be connected in cascade. So it will be XK, XK minus 1, XK minus 2, and these are all triggered by a common clock. So basically, okay, how much time it takes from the present value to go here? Obviously, it will take one clock cycle. This clock cycle is actually, we call it a tau. Okay, a tau. So tau is the time period of the clock, or it is also the delay in propagating the signal. Okay, at every stage in propagating signal. So we can say another way that this shift register is serving as the delay element or delay unit. It is serving as a delay element or delay unit. Delay element or delay unit. So it will be XK, XK minus 1, XK minus 2. Basically, each tau is a practically it is nothing but a shift register. It is nothing but a shift register. Clear? So when we get various samples that are stored at every stage of the shift register, we can multiply them with the corresponding values of H. We can multiply them and they will be added to get our particular output YK. So how to implement then the convolution, this convolution sum? So next thing is realization of convolution sum. How we will realize it? Let's see. First, it will be, there are something to write. I am not writing or drawing here. I start here. Say 1 tau. Say this is XK. Then another tau. This is XK minus 1. Then another tau. This is XK minus 2. There is then XK minus 3. This way it will be there. Okay. and this xk is the present value, present input. Okay, and all these inputs, these, that, these are the past values of xk, values of xk. Clear? And if we have delay element previously, then what we will get? We will get xk plus 1. That's the previous value. We start our observation from that point, but before we start our observation, something might happen earlier. So this is the, okay, so these are the things. So ultimately, this is the present value, these are the past values. So it will be what? It will be a future value, the next value. The next value is waiting here and it will come later. Okay, it is waiting there in the queue. Okay, so ultimately it is what? Then another tau is there. So these are all, actually it is xk plus 2. So these are all, we can say, future values. Future values of xk. These values, okay, with respect to present value, these are the past and these are the future values will be there. Okay, and why we are writing it? Because if you see convolution sum, our, okay, it is for any k we are getting it, k is varying from minus infinity to plus infinity, anything may happen. So that's why you are getting this particular thing. K may be positive, negative, anything. So in general, that is this. Now note that when we put n equal to 0 here, what happens? It will be xk into h0. When n equal to 1, it will be h1 into x k minus 1. When we put n equal to 2, h2 into x k minus 2. So ultimately it will be what? That xk will be multiplied with h0. xk minus 1 will be multiplied with h1. xk minus 2 will be multiplied with h2. And xk minus 3 will be multiplied with h3. This will be multiplied with h minus 1. And that will be multiplied with h minus 2. Okay. And ultimately they are added. This xk into h0 plus xk minus 1 into h1 plus xk minus 2 into h2. These all will be added. These are all added. So these are all added here. Okay, so and our output is yk. This is our output. Okay, so this is actually called the tapped delay structure. Tapped delay structure. Okay, of filter. Tapped delay structure of filter. We are taking a tapping from the various samples of input. We are taking tapping, and the tapping is taken from various delayed version of the samples. So it's a tap delay structure of filter. But for this particular structure, there is a problem. This filter cannot be realized in practice. Why it cannot be realized? What is the requirement of practical realization of this filter? Let's see this thing in the next page. Clear? Okay. So practical, so we can write it that practical realization of the relation requires that there are two requirements. One is the summation to finite number of terms, which means applying some approximation to the relation. So it means what? In the convolution, actually, we are multiplying up to infinite number of terms. So we need infinite number of samples, considering all future values and past values. So infinite number of samples will be multiplied and added. Obviously, we cannot work with infinite number of samples. So our number of samples will be reduced to finite number of terms. Our number of sample must be reduced to finite number of terms, and then they will be summed up, they will be added. So summation to finite number of terms, okay, is required. That is our first requirement. And we want to investigate how we can do that thing. Second thing is our Hn to be causal. Hn to be causal. That is, our Hn equal to 0, we can write for n less than 0. Okay. So it means that in the previous case also we see that it is h minus 1, h minus 2, h minus 3. Okay, these are the multipliers actually, but we cannot multiply anything with the future value. It's not possible. So Hn must be causal. After we get a sample at some present instant, then only it will be multiplied. So all the present and past values will be multiplied, but future values cannot be multiplied. So h of negative is not possible to realize at all. Okay. So that is the second requirement, that it must be a causal filter. Okay, it must be a causal filter. So how to realize that, and what will be its implication after making it causal? Okay. So now we see our first requirement. First requirement, that is summation to finite number of terms. So you want to truncate the filter. Okay, there will be not infinite length of the samples and h also impulse sequence. Okay, so how it's possible? So write, considering m number of finite terms. Okay, so we assume that m is even. So assuming m to be odd, we consider odd. Obviously for even, what will be the result? We'll see later. Odd, the truncated means reduced value. The truncated Hn extends from n equal to minus m1 by 2, okay, to then 0, then 2 plus m minus 1 by 2. So what will be our h then? So our Hn versus n will be something like this Hn So this is H0, H1, H minus 1. This way ultimately we will get here H m minus 1 by 2. It is m minus 1 by 2 and it is H minus m minus 1 by 2 or minus m minus 1 by 2. Clear? Now if we consider, say, m equal to 7 here. So m equal to 7 means it will be what? 7 minus 1 by 2. So 4 by 2, 6 by 2. So H0, H1, H2, H3, here H minus 1, H minus 2, H minus 3. This way it will be there. Okay. So it is our truncated real and symmetrical impulse response. Okay. Now we consider that our Hn, therefore we consider that Hn to be real and symmetric. What we will get? So assuming Hn to be real and symmetric, our previous relation, okay, becomes what? We write yk cap equal to summation hn x k minus n. That our convolution, this hn x k minus n, n will be from minus m minus 1 by 2 to plus m minus 1 by 2. So n is varying from minus m minus 1 by 2 to plus m minus 1 by 2. Okay. So where yk is an estimate of yk. Obviously, yk cap will be the estimate of yk. They are not exactly same. It will be different. Yk will take that new value yk cap. Okay. Then what will be the corresponding frequency response of this particular filter? Okay, let's see that thing. I write it in the next page. Page number 3. The corresponding frequency response is, now what is the expression of frequency response? Just I want to show you this one, that h omega equal to hn to the power minus j tau omega. So that is the frequency response. So here also it will be same thing. It will be h cap and hn cap. Okay, that will be there. Something like, or hn cap is not there, simply hn, but it will be up to finite number of terms. So h cap will be that one. So once we get that estimate yk cap, from we can get here also a frequency response h omega cap equal to summation, okay, hn e to the power minus jn tau omega, where n is varying from minus m minus 1 by 2 to plus m minus 1 by 2. That one. Or we can write it here as hn e to the power minus jn tau omega, n is varying from, okay, these two, minus 1 plus our h0 term e to the power 0 is 1 plus summation hn e to the power minus jn tau omega. Okay, and n is equal to +1 to m minus 1 by 2. That way we are getting it. Clear? Now exactly the similar way we can proceed. First we just apply commutative property, means we interchange this upper and lower limit here, plus h0 plus hn. Now we can write it h minus n here, e to the power plus j n tau omega. So n will be equal to 1 to m minus 1 by 2 plus h0 plus hn e to the power minus j n tau omega. So here we can apply our symmetry property. Okay, here our symmetry property is there. That is hn, h minus n equal to hn. This is our symmetry property here. Okay, maintained. So same thing here also we can write summation hn e to the power j n tau omega. Rest part is same. So as usual. Now we are writing h0 plus taking common h1 e to the power j n tau omega plus e to the power minus j n tau omega. This one. So it is what? E to the power j theta plus e to the power minus j theta. So 2 cos theta. So it is 2 summation hn cos n tau omega, n varying from 1 to m minus 1 by 2. Okay, so that is our h cap omega. Okay, so this is that frequency response is a real quantity. Okay, where h cap omega is an estimate of h omega. It is an estimate of h omega. So here also you are getting a real frequency response. We are getting a real frequency response. So our first requirement is fulfilled, that even when we truncate the finite, truncate the impulse sequence up to finite number of terms, okay, with symmetric impulse response, the frequency response still remains real, Okay. Then we want to go to our second requirement. Second requirement is that hn will be causal. So second requirement. Let's go to the next page. So next thing is second requirement. Here hn, okay, to be causal. To be causal. Now, what is that? To make hn causal, okay, let the impulse sequence, okay, be delayed by m minus 1 by 2 delay units. Delay unit means here our sampling period or clock cycle. In one clock cycle, one sample is taken in the register. So 1 clock cycle means it is the sampling cycle or sampling period. So here 1 unit is tau. Okay, the sampling interval or period. Okay, so what it is there, therefore, let's draw this thing, our Hn versus n. Okay, it is H0. It is here, it is actually m minus 1 by 2. Okay, so actually it is 3 here, we take m equal to 7. So it is minus m minus 1 by 2 or minus 3. Okay, so it is h m minus 1 by 2 and here h minus m minus 1 by 2. Clear? This one. So this is actually our truncated real and symmetric impulse sequence. Get my point? And this is delayed by, it is delayed by 1 to make a delay so that all the negative part will come to the positive side. So it is delayed by m minus 1 by 2. So if it is delayed that one, that h minus m minus 1 by 2, that part will become h0. Then the next value will become h1. Then another next value will be h2. This way our whole thing will be delayed. And finally it will be what? We call it HL versus L. So it will be so it is 0. So this is our H0. When we introduce a delay 0, 1, 2, 3. So this way it will be 3 actually. 3 or it will be m minus 1 by 2. Okay. And it will be 7. That is H7. Sorry. It is H6. M minus 1. H6. So H0 through H6. So it will be H m minus 1. That is this particular thing. So here also it is m equal to 7 and this is H m minus 1 by 2. Okay. So it is delayed. We can write it is delayed. Okay. And truncated real and symmetric impulse sequence. Okay. So therefore it is the pictorial representation. So we write let the delayed impulse sequence be HL, where now what is the relation between L and N? L equal to N plus M minus 1 by 2. Note that when N equal to 0, this N, when N equal to 0, L will be what? When N equal to 0, this sample will be H M minus 1 by 2. M minus 1 by 2. When N equal to M minus 1 by 2, it will be what? That sample. For L, it will be M minus 1 by 2 plus M minus 1 by 2. So M minus 1. Similarly, when N equal to minus of M minus 1 by 2 here, then L will be 0. This. So this thing will become 0 here after the delay operation. So here what happens? So now the thing is here symmetry is Here symmetry property is H n equal to H minus n. But in that case, our symmetry property, what it will be? What is the symmetry property? So we have to work out that symmetry property for this particular thing. So our next thing is symmetry property of HL. We want to investigate. Okay. Now so before time shifting or before delay operation, we know it is Hn equal to H minus n. Okay. Now after shifting by m minus 1 by 2 units, we are just introducing a delay of m minus 1 by 2. What it will be? So it will be Hn plus m minus 1 by 2 equal to H minus n plus m minus 1 by 2. So we are introducing equal amount of shift. Before shifting, that is the symmetry. After shifting by m minus 1 by 2 delay unit, we are adding m minus 1 by 2 in both the cases. That is this. Now, so we just put L equal to n plus m minus 1 by 2. Then what will be in the left hand side? It will be HL. In that side it will be what? H. Now minus n means what? Minus L plus this. So minus L plus m minus 1 by 2. So if you take n in that side, minus n equal to minus L plus this. Okay, plus m minus 1 by 2. Or it will be HL equal to H m minus 1 minus L. So that is the new symmetry. New symmetry property. New symmetry property of HL. New symmetry property of HL. We can check it. You put L equal to 0, so H0 equal to H m minus 1. You see here H0 equal to H m minus 1. Put L equal to 1. H1 equal to H m minus 1 minus 1. So H m minus 2. So H1 equal to H m minus 2. This way. So ultimately this is the new symmetry property of HL. Okay. Now our HL is a causal sequence. This is causal. This is not causal. Hn is not causal, but HL is causal. Okay, and its symmetry property has changed. It is something a different one. Okay, so we can write what? This symmetry property. So I write for page number. This relation signifies a symmetry property of a causal filter whose impulse sequence is HL. Is HL. Impulse sequence is HL. Okay, so that is this. So it is the symmetry property of a causal filter. Now, how to realize that filter after causality is maintained? So next thing is realization of a causal digital filter with filter of finite length. Okay, so that one. So what is the filter output? The filter output sequence may be expressed as yk bar equal to HL x k minus L, L equal to 0 to m minus 1. Note that in previous case our n was varying from minus m minus 1 by 2 to plus m minus 1 by 2. That is our thing. Already I showed you. N is varying from minus m minus 1 by 2 plus m minus 1 by 2. This thing. Okay, with respect to 0. But after we introduce a shift by m minus 1 by 2 amount, our N will be varying from 0 to m minus 1. 0 to m minus 1 for this thing. It is a causal filter now. So our Y will be different now, not same. So we are not writing a cap, we are writing a bar indicating that these output will be somewhat different. Okay. So for k equal to 0, 1, 2, all such things. Okay. Obviously here we know that L varies from 0 to m minus 1. Okay. And our HL is so we can write with HL as causal impulse sequence. Now let's draw the tap delay structure of the filter. So it will be so 1 tau, this is xk, then xk minus 1, then another delay unit, then xk minus 2, so this way it will go to a tau of is what it is. The last term is xk minus of m minus 1. So xk minus m plus 1. Minus of m minus 1 means minus m plus 1. And when our L equal to 0, then H0 will be multiplied with xk. So H0 will be multiplied with xk. When L equal to 1, then H1 will be multiplied with xk minus 1. So H1 will be multiplied with xk minus 1. When L equal to 2, then H2 will be multiplied with xk minus 2. So this way it will be there. And finally, when L equal to m minus 1, so xk minus m plus 1 will be multiplied with h m minus 1. And now they will be all added. And this is our yk bar. আর চিকেন বা পুরনো গরম না করলে ভালো কিন্তু অল্প না দেবেন 2 পিস চিকেন মানে মোট 3 পিস চিকেন পুরনো একটা নতুন দেবেন so that is this so it is figure is tapped delay structure of FIR digital filter. Okay, here symmetry of HL is not used. Now FIR means actually as the duration of the impulse sequence or impulse response is finite, as the duration of the impulse response is finite. So only it is up to h0 to hm minus 1, not after that, up to finite number of terms. Therefore, it is called finite duration impulse response filter. Of the impulse response is finite. Okay. It is called finite duration impulse response. In abbreviation, it will be FIR. Okay, digital filter. Okay, finite duration, so FIR, digital filter. And what is the number of multipliers here? This is one multiplier, second multiplier, third multiplier. So it will be mth multiplier. So number of multipliers equal to m. Number of multipliers equal to m. Clear? So that is the structure, tap delay structure of FIR digital filter. There. Our next task is to exploit the symmetry property. Here, there are some symmetry, that is the value of H0 and Hm minus 1. They are same. Say H0 and Hm minus 1 same. The values of H1 and Hm minus 2 is same. Value of H2 and Hm minus 3, they are same. So these symmetry properties are there. So we want to exploit this symmetry properties so that our mathematical manipulation can be reduced further. Mathematical manipulation. Now, what is the advantage of reducing mathematical manipulation? Means our processing will be faster. Our calculation will be faster. Okay. So we can handle large number of data, or we can get the output faster. Okay. The amount of hardware resources used will be also smaller if the mathematical computation is reduced. So that's why we want to utilize the symmetry property. So I'll show you how in the next page. So now it will be page number 6. So our next thing is direct realization of causal FIR digital filters with symmetric impulse response. Symmetric impulse response. Now the output is already known. It is yk cap, yk bar equal to HLX k minus L. L is varying from 0 to m minus 1. Okay. For k equal to 0, 1, 2, this way. Okay. So that is the usual relation. Now here number of multipliers involved is m. Here number of multipliers, okay, required is m. What is m? M is the length of the filter coefficients. It is the size of the filter coefficients. Okay. Now we consider the symmetry property now. So considering the symmetry property, HL equal to H, M minus 1 minus L. Okay, assuming an odd M. Our M is odd here. The input output relation, okay, may be expressed as, what is that? Yk bar equal to, now this enters 0 to M minus 1. So what we do? First we take 0 to, so it is M minus 1 by 2, and it is what? It is M minus 1 by 2 minus 1. So this is M minus actually 3 by 2. So this is what? Just 1 before. So M minus 3 by 2, that one. And what is that? It is M minus 1 by 2 plus 1. So it is M plus 1 by 2. So just the previous of the center value and the next of the center value, these are marked that particular bit. So we are adding from 0 to M minus 3 by 2. Then M minus 1 by 2 is kept separate. Then we are again start our addition from M plus 1 by 2 to up to rest of the term. So 0 to M minus 3 by 2 and M plus 1 by 2 to M minus 1 plus the central term. So it will be, so it is HL X K minus L. L is varying from 0 to M minus 3 by 2. Just it is before the central term. 1 before central term. Plus H M minus 1 by 2 X K minus M minus 1 by 2. Okay. Plus summation HL X K minus L, where L is varying from just after the central term, M minus 1 by 2 plus 1. So it will be M plus 1 by 2 to up to rest of the term. Okay. So substituting HL equal to H M minus 1 minus L in the last term. Last term is this term. This term, last means this particular term. Last term. What we get? Summation of HLX K minus L, L equal to M plus 1 by 2 to M minus 1. Here we are writing it summation H, L is replaced by M minus 1 minus L. Okay. Other things remaining same. X K minus L. Okay, that is this. Now we just introduce some substitution. We write L minus M plus 1 by 2 equal to some P. So let L minus M plus 1 by 2 this equal to P. Then the last term is this one or that one or this one, becomes what? It becomes, we write it, note that it is H, now M minus 1, then minus L means what? It will be M minus 1. Now if we take L in the right side, it will be what? Minus P minus. Okay. So H, M minus 1 minus P plus M plus 1 by 2. So just we are substituting L in that particular expression, this L here. We get that thing. And X, K, okay, Xk minus, now L means this particular, it will be P plus this. So it will be P plus M minus 1 by 2. And note that when L equal to M plus 1 by 2, P will be 0. And when L equal to M minus 1, then M minus 1 minus M plus 1 by 2. So P will be equal to, if you calculate, you'll get M minus 3 by 2. So this particular term. Okay. Or it will be what? Summation P is varying, just we are changing the limit. Okay. So that this limit is same as that limit, that particular thing. So A P equal to M minus 3 by 2. H. Now we can write M minus 1 minus M plus 1 by 2. So it will be H M minus 3 by 2 minus P, that particular thing, into X, okay, K minus P plus M minus 1 by 2. It is not simplified anymore. Okay. So that is this particular thing. Now again we want to make another substitution. Okay. So let's see what is that. We want to substitute with one single variable, just like this one, just like here H of L, a single variable, here also H of thing. Let's see what happens. So H of, so you're adding Q. So we just consider this M minus 3 by 2 minus P equal to Q. Let's see what happens. So I write it in the next page. Page number 7. Page number 7. So it is equal, let Q equal to M minus 3 by 2 minus P. So this one, Q equal to M minus 3 by 2 minus P. Okay. Then the last term becomes, last term becomes okay. So it becomes what? So it is HQ. So it is HQ and K minus, it will be what? In place of P, you will substitute it in terms of Q plus M minus 1 by 2. Okay. So it is HQ, then X, K minus, in place of P, what it will be there? If you take P in that side, it will be M minus 3 by 2 minus Q. Okay. So it will be M minus 3, say in place of P, it will be just Q will be there plus M minus 1 by 2. So in place of P, it will be M minus 3 by 2, okay, minus Q plus M minus 1 by 2. Okay. That is there. And note that when P equal to 0, the lower limit, what will be the value of Q? When P equal to 0, our Q is M minus 3 by 2. And when our P equal to M minus 3 by 2, when P equal to M minus 3 by 2, M minus 3 by 2, Q will be 0. M minus 3 by 2. Clear? So that is this particular thing. Okay, we are getting it that particular way. Now a little bit of simplification is required. So it will be just we are interchanging. Sorry, there is a mistake. It will be 0 when q equal to m minus 3 by p equal to m minus 3 by 2. You put it here, m minus 3 by 2. Q will be 0. So 0. So now what happens? We are interchanging the limit just by commutative property of summation 0 to m minus 3 by 2. So the limit does not change actually, but it is HQ x. Now if you simplify, you will get m minus 3 by 2 plus m minus 1 by 2. So ultimately it becomes k minus m minus 1 minus q. So if you add them m by 2, m minus 3 by 2 minus half. So minus, okay, so ultimately it is m minus 1 by 2. M minus 1 minus q. Clear? Sorry, it is m plus 1 by 2, 1 minus. That's why it was not matching. Okay. So that is our last term. Now q is just a local variable in the summation sign. So we can just replace q with L. Okay, so you can write it. If it is L, it will be HL x k minus m minus 1 minus L. So in place of q, it will be L. L equal to 0 to m minus 3 by 2. So what is that part? This is the last term. The last term, L. So this is actually equal to this our last term. Okay, so now we write yk bar equal to this term plus that term plus our last term. So I write it here. Similarly, yk bar equal to that term. So yk, okay, so therefore, thus the expression of output becomes yk bar equal to summation HL x k minus L. Plus h m minus 1 by 2 x k minus m minus 1 by 2. Okay, plus now this term we are writing that thing. Summation L is 0 to here m minus 3 by 2 HL x k minus m minus 1 minus L. This term we are writing it. Yeah. So or we can write it yk bar equal to, now we are taking common. So it will be just summation L equal to 0 to m minus 3 by 2 HL into xk minus L plus, now this term x k minus m minus 1 minus L, that one, plus it is h m minus 1 by 2 x k minus m minus 1 by 2, that particular term. Okay, so that is our relation. So you see what happens actually, we are adding just 2 samples first and then we are multiplying. So number of multiplication is reduced. So number of multiplication will be what? In previous case it was number of multiplication was m, in m number of coefficients, but here number of multiplication is reduced. It is 0 to m minus 3 by 2 means number of multiplication is m by 3 by 2 m minus 3 by 2 plus 1 actually. So number of multiplication is actually m minus 1 by 2 plus 1. So it will be actually m plus 1 plus 1 more multiplication this way. So it is m minus 3 by 2 plus 1 plus 1. So it is total is m plus 1 by 2. So it is greatly reduced, almost half. So what will be our tab delay structure then? I draw it. Xk, then tau, xk minus 1, tau, okay, xk minus 2, then we are writing here tau. Okay, now our middle term is what? 0, 1, 2 up to our middle term is m minus 1 by 2. So this is our just this m minus 1 by 2. So xk minus this term m minus 1 by 2. Clear? That particular thing. After that, the next term will be this plus 1. Okay. So plus 1. So it will be xk minus of m plus 1 by 2. If you add plus 1, actually one more minus 1. So minus 1, minus 2, minus 3, minus this, then minus 1. It will be m plus 1 by 2. So k minus m plus 1 by 2. So this way it will proceed again. And then it will be what? So one more tau. Then it is what? One more tau. Note that here the last term is what? Last term is so it is x. You put L equal to m minus 3 by 2. So actually it will be if you put L equal to 0, so it is xk. You put L equal to 0, it will be xk minus m minus plus 1. So it is xk minus m plus 1. This is the last term. The previous one will be what? Put L equal to 1. So xk minus 1. Similarly here xk minus m minus 1 minus 1. So it is xk minus, okay. So it is xk minus plus 2. K minus m plus 2. That is m minus 2 actually. This way it will be there. Okay. Now note that our here L equal to 0 is acting as a multiplier. So first xk. Now you see, we put L equal to 0. Then xk is added with xk minus m plus 1. So xk is added with xk plus m plus 1. So they are added. They are added. After addition, they are multiplied with h0. After addition, they are multiplied with h0. Again put L equal to 1. So xk minus 1 and xk minus m plus 2 will be added. Okay, so they will be added. So it is added. And the result will be what? The result is multiplied with h1. This way, this pair, this thing will be added with that one. So the previous term is what? It is xk minus m minus 3 by 2. That one is added with that one. And it is added, it multiplied with h m minus 3. Put L equal to m minus 3 by 2. So it will be multiplied with that particular thing. And the middle term, that is h m minus 1 by 2. So it will be added with h m minus 1 by 2. Will multiply it. So after multiplication, what happens? Okay. So it is that one. These are all added. So these are all added. Okay, and the result is this is our yk bar. Yk bar. So this is the tap delay structure of FIR. So tap delay figure, tap delay structure of FIR digital filter with symmetry in impulse sequence. HL. Okay. And number of multiplier is what here? Number of multiplier equal to m plus 1 by 2. H0, H1, H2 up to, okay, m plus 1 by 2. Now for even n, for even m, if m is even, okay, number of multiplier equal to m by 2 will be. Can be proved. Sorry, it is not clearly visible. Number of multiplier is m plus 1 by 2 for odd m. For even m, it is m by 2. You can check if you think little bit, you will get that it will be m by 2. Any question? Today I want to conclude with this particular thing. Any query? No. Okay. So now better we stop.